Skipping some details. Let us start, but let us start with one rather simple but important observation, namely how to see Poincare duality from the viewpoint of Morse functions. It is very useful in itself, and it will also be needed to us. Suppose that we have already discussed that we always, on any closed manifold, compact without boundary, we can always organize a Morse function such that it is self-indexing. All critical points of index lambda are on level lambda. So, then we have discussed that we immediately obtain a chain complex which gives us homology of our manifold. Namely, if we have critical points of index lambda plus 1, and we have critical points of index lambda, then we can compute for each pair of such critical points. We can compute number of course, we always consider a gradient-like vector field, then we obtain trajectories of this gradient-like vector field. In general position, we can always organize so that left-hand spheres and right-hand spheres are transversal, as we usually did. And then we just compute number of trajectories with signs, algebraic number of trajectories. This is called incidence coefficient, and we get immediately chain complex associated with this Morse function. C lambda plus 1 is free abelian group generated by this. C lambda R is free abelian group generated by critical points of index lambda, and we immediately get differential boundary operator, which is given by this formula. We have discussed this last time. Then d squared is equal to 0, and the homology of this chain complex is just usual homology of our yes, coefficients will always be the usual homology of our manifold Wn. Well, that's general picture, but what can we do now? Now we can swap this picture, swap the direction of this part. So we can replace function f with function minus f. What happens then? Let us denote points of index lambda become points of index n minus lambda. So what do we actually see? We actually see that let us denote the corresponding groups by the corresponding chain complex with prime. So initial chain complex corresponding to function f is c star, chain complex corresponding to function minus f is c prime star. To be honest, not minus f, but n minus f. update the self-indexing again. What then we see? How the differential in this complex is organized. Look, we count the same trajectories, but now they are trajectories from P to Q, not from Q to P. But we count them, and so this d prime is now d prime of P is now sum of over Q. The same incidence coefficients times Q. What does it mean? This means that if we naturally identify C lambda with C prime n minus lambda, we can identify that these are just abelian groups with the same basis. Yes, they just coincide by our definition. Then we get that the delta here and delta prime here just are adjoint to each other. Where they are adjoint if we consider these standard bases as orthonormal, are adjoint to each other if we consider bases of critical points orthonormal. However, actually, no scalar product is needed here. It is the same thing can be said in more invariant terms. Actually, a better statement assertion is that Cn minus lambda prime is naturally isomorphic to the dual of C lambda. And then we do not need any metric, and then we just it is better to identify. We have in all this stuff we have 3 abelian groups with prescribed bases. For prescribed bases, we can swap between group and its dual as we want. But here this identification is better, since then we can say about adjointness without any metric. They are adjoint, and what we see immediately that this is not only isomorphism of groups, but this is isomorphism of chain complexes. Chain complexes C star. C prime is isomorphic to home from this. But here it is better to write in this way. Yes. What do we know very well that if we consider the standard definition of cohomology is that we take chain complex, we take its dual, and we take the homology of the obtained chain complex. Yes, this is called cohomology of the original split. So this is just cohomology, and this is homology. And we immediately obtain isomorphism that cohomology of dimension n minus lambda of our W are isomorphic to homology dimension lambda of the same chain W. So this is a rather nice situation and rather nice viewpoint on graduality. It can be just directly read from Morse function. Yes, I want to make two comments here. First of all, we will often want to work not with closed manifolds, but with, as usually, manifold with two boundary components, V and V prime, such that V is on the same level below 0, V prime is on the same level above N, and all the same, and no critical points on the boundary. What we will see in this situation? All the same, completely the same argument works, but what we get? In this, we have discussed that in this situation, this chain complex gives not the homology of W, but relative homology of pair W, V. Let it be V0 and V1. W, V0. Well, but that complex, when we swap direction, then it is related to the pair W, V1. And using completely the same argument, we arrive to the following theorem, that cohomology of dimension n minus lambda of pair W, V1 are isomorphic to homology of of dimension WV0. Sorry, this comment was supposed to be the second comment, and first comment is as follows. In all this stuff, in all this, I was not careful enough about signs. Namely, these incidence coefficients, these signs were defined using some orientations of left-hand disks. When we swap direction, left-hand disks turn to right-hand disks, and generally we have some signs. And so it is, I would like to left this as an exercise. Just be careful about signs in this definition. The most important is not the fact that here sign is 1. If we make some natural conventions about orientations, then sign will not be 1. An important thing is that this sign is actually depends only on dimension. And if we just change differentials by some sign depending on the dimension, then homology doesn't change. So what is important? It is important that signs which we get here depend only on dimension, only on индекс of critical points. Окей.
Извините, а вот здесь у нас получается, что W должно быть ориентировано.
Sorry, but graduality is of course, for only orientals. Thank you very much. I forget to say from the very beginning, of course, no point graduality for non-orientable manifold, just we have no point graduality.
Где мы пользовались ориентацией? Когда знаками?
In this particular case, actually, we would like to come from left-hand disks to right-hand disks. if we do not have any orientation of an ambient manifold, we cannot obtain orientation of left-hand disk from orientation of right-hand disk or vice versa. If we have, then we can do it, and we get some sign which depends on the data. Well, and second observation is that another part of this theorem is that instead of saying that we have this isomorphism for between cohomology and homology, we can say that there is pairing between homology and homology. There is some at least bilinear pairing. Which is non-degenerate on free paths. Generally, these are abelian groups. They consist of some free path and they consist of some torsion. I don't want to discuss torsion now, but on free paths it is non-degenerate. Non-degenerate on free paths. This follows immediately from this isomorphism. The matter is that natural pairing between cohomology and homology of the same dimension is non-degenerate on free paths. This is just standard algebraic topological fact. But what is important for us now is that what is the geometric meaning of this pair? Look, how does the lambda homology look like from the viewpoint of Morse function? We have lambda's chain group, and it is generated by these left-hand disks. Well, these left-hand disks, when we start filling this bottle, when we go from down to top, when we cross this level where these points live, then we attach several cells from homological point of view. We attach several lambda cells, and these are exactly left-hand disks of these critical points. Further, we obtain only on some cells of higher dimensions. So lambda homology can become less. We take quotient of it by some lambda plus first. But so any homology class can be represented by linear combination of these cells, of these left-hand disks. What happens when we study this homology group from the viewpoint of the same function, but with swapped orientation? For the reversed function, these critical points are points of index n minus lambda. For the initial function, they have index lambda. For the reversed function, they have index n minus lambda. And instead of right-hand disks, we have left-hand disks here. What do we see? We see that any n minus lambda class here, so any class here, is linear combinations, some linear combination of this red left-hand disk. Any class y here is linear combination of two disks. And what is geometric meaning of this pair? This is just algebraic intersection number. If we look through this construction, then we see that actually we say that this basis is orthonormal. This exactly means, but these are actually that this is has intersection has pairing one with that disk. So this is exactly algebraic intersection index. And this is important viewpoint, and it will be useful to us now. Okay, this is about concurrent duality. Well, now there is one important theorem.
Можно вопрос?
Yes.
А вот если у нас есть учение в гомологии, то это странно получается. Мы если как бы возьмем и умножим на 2, скажем, одну из компонентов, то вроде бы индекс алгебраически тоже на 2 умножится.
Все, что лежит в включении, будет иметь индекс как 0.
И спариваться.
И спариться будет нулем, там другое спаривание. Включение. Okay. Let us discuss the following. Now let us for a moment forget about this, but I will return to this in one moment. Actually, what I wanted to say, if we have this picture of a manifold with self-indexing Morse function, well, we can always cut this manifold into pieces, cut this cobordism into pieces, so that each piece has critical points with only one critical value. Just make cuts on all levels between. So let us now study some piece where we have only one level of critical points, only one index of critical points. So now I would like to study this situation. So suppose now that we have the following situation. We have again V0, V1, W, and we have only one type of critical points. All critical points have the same index lambda, and all of them are on the same level. And what do I want? In this situation, our chain complex is very easy. It consists of a single group. So, relative homology. Suppose that we have S critical points here, then relative homology of W V0 is isomorphic to Z to the power S, and all are trivial. And this group is generated just by those critical points, by left-hand disks of critical points. Okay, this is the initial situation. What do we want? The matter is that, okay, we have these left-hand disks provide a basis for this group. Well, but this group, this homology group, is completely independent on the Morse function. It depends only on this triple W V0 V1. This group knows anything about Morse function. So, but Morse function provides a basis for this. It is a natural question. assume that we have an arbitrary basis here. Can we modify our Morse function? Is exactly that basis. So once more, if we have a Morse function, then we obtain a basis in this group. The group itself is independent of the Morse function, but the basis is dependent. Question. Vice versa, assume that I have taken an arbitrary basis of this group. Can we organize a Morse function with this property, with the only with all critical points of index lambda on the same level, so that this basis is the basis of the left-hand distance? And the answer is yes, but as usual under some conditions. Are very simple. So here, it's lambda and lambda on the same level. Assume that lambda is between. Also assume that yes, be an arbitrary basis of this group. Claim is that we can modify, so we start from Morse function and gradient-like vector field. We can modify them so that we obtain new Morse function and new gradient-like vector field with the same property. Again, all critical points have index lambda and are on the same level, but with the same property, and such that the basis of left-hand disks for this new function just coincides with the prescribed basis AI. Well, yes, and also I can say that f prime c prime coincides with the initial pair near the boundary. So we change somewhere in between, but near the boundary everything remains. This is an important theorem, which allows us to reorganize a basis consistent of this. Of these disks as we well, let us prove this theory. I will skip some technical details. Actually, I will now draw a picture and explain it from this picture. It is more or less standard to prove this. But okay. First of all, what we want to prove? It is very hard to prove something about an arbitrary basis, but we know very well that there is the following algebraic fact, that any two bases of such free abelian group can be transformed one into another by elementary moves. Which elementary moves? First of all, we can change sign of any basis element. But actually, when I say that these disks form a basis, actually I always need to say that these disks being properly oriented gives us a basis. So we have freedom to choose orientation of these disks. So this elementary move is immediate. We can organize it just by reversing it. And the second type of elementary move is that if we have if we have such a basis, E1, E2, ES. Then we can change it by bases where some I plus, II is on the I is replaced with the sum, the EI, EG plus EG. So this is standard elementary move for bases. And the only thing what we need is that if we can realize these bases by a Morse function, then we can realize these bases as well. If we prove this, then we are done. Since we can, or we, from the very beginning, we have a Morse function which realizes some bases. We want to realize these bases, but it can be obtained from the initial basis by some elementary moves. If we can handle each particular elementary move, then we immediately prove this. And of course, it is enough to take